Hey, in this video we're going to be talking about defining matrices. And I know we've defined some matrices before, but there are different ways to do it, and we have to deal with those as game developers. So we're kind of used to defining matrices. Let me try this one out. Here's a matrix. This is our friend, a translation matrix, 4 by 4. And we're used to defining it this way, and that's great. So if I wanted to define this in code, like in C++ or C# or some other C family language, I would probably make a variable, let's just call it a matrix. This could be something like a float array, and I would give it a name. It's Matt. And then I would initialize it. So using this common initializer syntax that usually works for C family languages, curly braces, I would want to put it in like this: 1, 0, 0. And then my tx, let me turn that into something, let's use dx, something that's more like what I would write in code. All right. So that looks pretty good. That's a good way to define a matrix. So if I were looking at this in terms of the memory order, how an index will progress through this matrix, I could also kind of note this matrix as, let's do like, that's a curly brace. It's sort of like index 0 is here, index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 16 different values. 15 is the highest index you get to. So when I'm looking at this, this is something that they would call a row major ordering. So this is fine. This is fine and natural. It looks like a matrix. I could use it. I could do that. But there's another way to do it too. Another equivalent way. So what if we did, instead of having our indices, say you have on a math whiteboard, you're going to have to kind of follow a convention of how to visit each of these values. But what if I wrote my indices instead like this: 1, 2, 3, 0, 1, 2, 3 going vertically, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so this is another way to do the ordering. This is called column major ordering. And it is perfectly fine. It's another perfectly fine matrix we could work with. The difference in these two is a convention. It's something that people agreed on in order to represent matrices in their code. So when you're working with matrices in code, you do need to know which of these conventions that they are actually using. One of them, row major ordering, kind of seems more natural, at least in my opinion. But column major ordering is still out there. It's still pretty popular. So we'll see some cases where this comes up. And if you look at these, they are really just transposes of each other. That is, you can swap the rows of one with the columns and arrive at the other one. Or another way to do transpose is to just flip things around the diagonal. So if I flipped the column major ordering around the main diagonal, you'd end up with a 1 where the 4 is, a 2 where the 8 is, a 3 where the 12 is, and they would swap places. So the 12 would be where the 3 is right now. And so it would look exactly the same. Right? So they're just transposes of each other. Now, to me, it seems like the first one makes the most sense, row major ordering. As you increment the index, you're iterating first through a vector stored in the first row. So here's my matrix, and we are going this direction through first a row vector. And then we go to the next row vector, go through it, next row vector through it, and then the final row vector. This is how we iterate through all of the elements of this matrix. In column major, we go kind of a different direction. If you want to go through the x, y, and z components of the first vector, you go down the column first, then back up to the next column, and then back up to the next column, and then to the final column. Right, so now because they're transposes of each other, we have to understand that sometimes you'll find online, looking at matrices, you'll find them in either row major or column major order. The most common is row major. This is what we see in math class. However, as it happens, for reasons unknown, it may be lost to history, OpenGL, the graphics library, uses this column major ordering. Microsoft's Direct3D, so here, OpenGL, Direct3D from Microsoft uses the row major ordering. So bravo for them. So if OpenGL uses column major, Direct3D uses row major, do we really care? Well, are we actually going to be working with matrices in low-level OpenGL code? Well, maybe, but even if not, Unity uses column major ordering, just like OpenGL. If you do some matrix code in Unity and you access individual matrix elements, you could set it up using a row major ordering, and that would work as long as you're consistent and you define your own way of setting up matrices and you do the multiplication yourself. That works fine. But if you rely on Unity's built-in stuff, you need to follow their convention, which is column major, unfortunately, I guess. So this idea of this convention, this ordering convention, it maps our sense of a matrix to its storage in computer memory. If you're not dealing with computer memory, well, then it really doesn't matter. You probably don't care about the indexing all that much. So this determines the order of our indices, what they mean when you just access an array in our code. And it has several real implications. So the first one is that when you're indexing using multi-dimensional arrays or 1D arrays that you're treating as a two-dimensional array, in column major, how many times I'm going to write this. You're going to be accessing like my matrix, and then the x, y, or z component index, 0, 1, 2, or 3, and then the choice of which vector. So that's the order you're going to be putting those indices in. Your component will come first, which vector you're dealing with comes second, and normally when you're looking at in terms of graphically representing these, usually this is the row first and the column second. So then when you do row major ordering, it's the other way around. So which vector comes first? That's the row vector that you're choosing, and then the column is the component index, 0, 1, 2, or 3. The second thing is that math matrices, the second difference here is that math matrices will look transposed. So when we had our translation matrix, we had something like 1, 0, 0, dx. I'll write it in using my programming notation now. 0, 0, 1, dz, 0, 0, 0, 1. All right. This would be the row major notation, and then in column major it would be transposed. So if you are defining it in code, you would actually have to write it out differently when you are entering this matrix into your code in column major. So just transposed, but it's important to know the difference. And when you're looking at things online, make sure that you know whether they're talking about row major ordering or column major ordering. And the last thing is that matrix multiplication is going to be affected. So we typically want to be able to just say like, here's a matrix A and here's a matrix B, and if B were like some sort of transformation, we might want to multiply B times A, just applying them that way. This is what we would like to have, because this is kind of the traditional convention in math. But when we do matrix multiplication, just straight out multiplication, say we have two other matrices, let me give them different names, U and V, and I want to multiply them. So in row major, we would just multiply as you normally would do in a math class, U times V, and we have a definition for how that multiplication happens. In column major, we would typically not do this post multiply. You see you started with U and you're multiplying V, so you put V afterwards. We would multiply on the left, pre-multiply or left multiply. That one's a V. So it's kind of the other way around. That's if you wanted to maintain the same definition of your matrix multiplication. But you can redefine this, and you can say, because they're just transposes, right, we can just multiply on the other side, on the original side, by using the transpose. So we could use U V transpose. That'll probably turn out right. But you need to be aware that matrix multiplication is going to be defined just a little bit differently for these different orderings. Now, it's going to get confusing sometimes. It can get confusing easily. So we're not actually going to spend a lot of time on it. We're not going to do a lot of this in code because practically libraries that define matrix multiplication will define it so that it always looks like you're pre-multiplying. It will always look like we're doing what we wanted all along, and it doesn't matter which ordering convention you're using. So in other words, if you're not messing around with individual elements of the matrix, you don't need to worry about any of this at all. But once you start poking around defining your own matrices or changing individual elements of the matrix, then this matters. All right, so in the next video, we'll talk about some other properties and important aspects of matrices. I'll see you then.